Hi, welcome back to example 4. And we're going to work on this differential equation. And we're going to do it by using the appropriate substitution. So one thing is that this is in the form of an exact equation. And if I check the m and the n, this is actually an exact equation. But because we want to see the substitution methods, we're going to solve this using a u substitution. Now, what looks simpler? Does m look simpler or does n look simpler? N looks simpler. Because n looks simpler, we're going to say y is equal to u x. And I'll go ahead and say what u is. U is equal to y over x. And I'm just going to check up here just to make sure and then we're going to also do the differentiation because we need to substitute in for that dy. So dy is equal to u dx plus x du. All right, let's go ahead and substitute in. So now we're going to use u substitution. So wherever there's a y, we're going to substitute with u times x, and we're going to substitute our dy with u dx plus x du. We're going to keep all of our x's there. So we're going to, over here on the left, we're going to stay x plus ux dx plus x times dy, and dy is u dx plus x du, and that's equal to 0. And now we're going to go ahead and I'm going to distribute this x into that. And so I'm going to get x plus u of x dx plus xu dx plus x squared du, so that equal to 0. All right, now I'm going to get all my dx's to the same part. Now notice here there's a ux plus a xu, which is also ux dx. So there's really two of those there. So I'm going to have x plus 2ux dx plus x squared du equal to 0. Now, I could choose to make this a separable equation if I wanted to. We're still going to do that, but what I'm going to do is I'm just going to get all my u's together and all my x's together. So on this left-hand side, what I notice is I can pull out an x and just get 1 plus 2u dx, and then plus on the right-hand side, x squared du equals 0. All right, now I'm going to divide everything by x squared, which is really just dividing this left part by x squared. And I'm going to get 1 over x dx. And on this right side, this du, right here, I'm going to divide by that 1 plus 2u. So then I'm going to get du over 1 plus 2u. Set that equals 0. That way I have all my x's together and all my u's together. Again, just to show you, I brought this x squared to divide by that x and keep that dx to give me 1 over x dx. And then on the the left part of the plus sign, I'm taking this 1 plus 2u and I'm dividing it into du. Now, we're doing it to the other side too, but since that's 0, it's not really going to matter because it's still going to be 0. So now, we have 1 over x dx plus du plus 1 plus 2u. Now we're going to go ahead and integrate. So I'm going to integrate each part. So integrating the left and the right. On the right-hand side, that 0 is just going to give me c. 1 over x is just going to be natural log of x plus, I have 1 over plus a du over 1 plus 2u, so that's just going to be 1/2 natural log of 1 plus 2u. And that's equal to c. Now let's go ahead and solve. So we're going to I'm going to put an exponential to both sides. And when I do that, the left-hand side, I'm going to go ahead and just bring this over right there. E to the natural log of x is just going to be x times, then I have 1 plus 2u to the 1/2 power, and that's equal to c. Alright, now what I can do, I can now change what my u is. If I change what my u is, then I'm going to get x times 1 plus 2 times, now our u is y over x, so y over x. And then I have 1/2 equal to c. So there's the equation solved. Now I can write that in a better way. So what I'm going to do is I'm going to square the left-hand side and the right-hand side. If I square the left-hand side, I'm going to get x squared 1 plus 2y over x is equal to c squared, which is still just going to be that constant c. And then I can distribute in that x squared. I'm going to get x squared plus 2y, or I'll say 2xy is equal to c. And we're finished there. All right, x squared plus 2xy equals c is the solution to our differential equation. Again, it's a potential solution. Doesn't mean it's the, the perfect solution, because it could be a little bit different. And the thing is, this actually could have been solved with an exact equations, and you'd get something that's a little bit different, but it's still in the same family of solutions. So that's why I call this a potential solution, because it's in the same family of solutions, but it's, not necessarily going to be the exact solution to what we have here, because if you take the partial derivatives, but we could manipulate this by using a constant, and we'd get this, and we'd get back to where we're at. So that's why that C put this in the family.